Hello, welcome to lecture 7 of the course. In this lecture and the next couple of lectures, we are going to discuss about the various representation of the quantum state of a system. We know that we can represent the state of a quantum system by using the so-called state vector or the wave function. However, there are many situations where we cannot define the state of a system by using state vector or wave function. In particular, in those situations where the system is interacting with the environment or the surrounding or with other systems. In those situations, we can define the state of a system by using the so-called density operator or density matrix. In this lecture and the next, we are going to discuss about the density matrix formalism. So let's begin. We know from postulates of quantum mechanics, and as we have discussed in lecture 1 in some details, that the state of a quantum system is represented by an object called k psi or the so-called state vector. Generally, we can represent the state of a system, say A, if the system is not interacting with environment. That means if it is a closed system, and if the system is a closed, that means if it is not interacting with surrounding or the environment, it is also termed as an isolated system. And as we have learned that this state vector or k psi contains all the information about the system A. However, many a times this system A is going to interact with the environment, and in such a case this system A is known as an open system. And for open system, many times we cannot define a state vector for it. In that case, how we can represent the state of an open system or such kind of a system for which we cannot define a state vector? To understand that, let us consider a two-state quantum system with basis states say kg and ke, and let us say we have an ensemble containing the two types of states in it. Let's say k psi and k phi. These are the two types of states we are having. These are arbitrary states, and because these are arbitrary states, I can write k psi as a superposition of the kg and ke. Kg and kt are the so-called ground state and the excited state of the system respectively, and the corresponding amplitude are say a1 and a2. These are the quantum probability amplitudes, and k phi can be represented as say b1 kg plus b2 ke. Okay, now if we ask this question, however, before that, another important point to note is that the system, we are not defining a single state vector to represent the system. Now the system can be represented by either k psi or k phi, and in this particular box the probability that you are going to pick up k psi is say p, and obviously the probability that you are going to pick up k phi is 1 minus p. These p are the classical probabilities. Now let me ask this question, that what is the probability that the system will be found in the ground state, that means in kg. Okay, so you may say that okay, it may be a1 mod square or b1 mod square, just by looking at these equations for k psi and k phi, but that is not going to be the correct answer. We have to answer it little bit carefully. First of all, what we have to do, we have to pick up the state from the box. So you have to pick up k psi or you have to pick up k phi, and you can pick up k psi with probability, classical probability p, as we have seen, and k phi can be picked up with classical probability 1 minus p. And after you pick up these states, what you have to do, you have to make a measurement, then you have to make a measurement on the picked up state, right? Picked up state. Okay, let me elaborate it further. And you have to make the measurement in the picked up state in the basis kz and ke, because this is going to be a quantum measurement now. Let's say you pick up this is very important to understand, that's why I'm writing it in some details. Say you pick up k psi, then the probability that because of the measurement, the probability that the state collapses to kz is, as you can see, k psi is given by this expression. Now when you make a measurement on k psi, the probability of getting kz, that means it is collapsing to the state kz, would be mod a1 square. Okay, so in fact, okay, that is not the correct one, because first you have to pick it up. So the correct answer would be p into mod a1 square. P refers to the probability that you have picked up k psi. And similarly, on the other hand, if you look at the case, if you pick up k phi, then the probability that the state of the system collapses to kz is, now picking up k phi from the box is 1 minus p, and once you have in k phi state here, the probability that it is getting collapsed to kz is mod b1 square. So it would be 1 minus p into mod b1 square. So I hope you get the idea here. Hence from here you can say that the total probability, of getting the system in the state kz is, first, if you have picked up k psi, then this is the probability. Then if you have picked up k phi, then this is the probability, 1 minus p mod b1 square, right? Similarly, the probability, you can immediately see, the total probability of getting the system in the excited state kate E is, again you can see that first you have to pick up, say if you have picked up kate psi, then the probability of getting the system in the kate E is mod a2 square. And if you have picked up kate phi, the classical probability of picking up kate phi is 1 minus p, and after that you make a measurement and getting the state in kate E is mod b2 square. So this is the total probability. So as you can see, here we are unable to specify a state vector k psi for the system under consideration, but we can represent in that case we can represent the state of the system by a new object. State of the system we can represent by a new object called density operator denoted by this symbol rho, and this is defined as rho is equal to p k psi bra psi. As you have seen that p is the classical probability of picking up k psi, and then you have 1 minus p, that is the probability of picking up the state k phi, and this is going to be represented k psi bra phi. So this is the so-called density operator, and This is basically a general way to represent the state of the system that we have considered here. Now we can actually extend this definition in general for the general case where we have many states in an ensemble pertaining to a given system. For example, suppose we have many states, type of states. Say we have psi 1, we have say kth psi 2. There are many types in a ensemble like this. Okay, the corresponding probabilities are, say, for psi 1 we have classical probability of picking it up is say p1. For psi 2 the probability is p2. For psi 3 probability is p3. For psi 4 the probability is p4, and so on. In that case we can represent the state of the system by this density operator defined as, say, p alpha, psi alpha, kth psi alpha, bri psi alpha, where p alpha is the classical probability associated with the state vector psi alpha, kth psi alpha, and with the condition that the total classical probability has to be equal to 1. So this is the definition, general definition of density operator, and this is valid for even a isolated or a closed system. Okay, and this definition is very general, and we will see its potential as we proceed in the lecture. Now, for the case of isolated system, or for the situation where, say, we have just only one state, only one type of state in an ensemble. Let us say we have just kth psi in an ensemble, or we have a collection of kth psi because it's the type is the same. So as you can see, every time you have to pick up, you are always going to pick up kth psi. That means that with 100% probability you are going to, classical probability, you are going to pick up kth psi. So therefore in this case the state of the system is going to be represented by the density operator kth psi bra psi. This is the state of the system, and this kind of a system or the state is known as pure state. Okay, and when you cannot represent the state in this form, this kind of states are, that means when you cannot represent it in this form, that means you represent it this kind of a form, say p alpha, psi alpha, psi alpha. This kind of states are called mixed states. So this refers to mixed state. Okay. We'll soon see how to quantify a pure and a mixed state. Before I proceed further, let me give you an example. Consider a two-level system as discussed in lecture 4 or so. There we have defined a two-state system kth psi, which is in an arbitrary state, and say this system is in isolated, and that means not interacting with environment. Then its state is given by superposition of kz, ground state, and the excited state kte, and the corresponding amplitudes are cz and ce. Now what's the density operator representation of the this particular two-state system? Because this is isolated, so this is going to be a pure state, and the fact that we are able to define it by a state vector kth psi, that itself means that it is an isolated system. And then we have the density operator would be kth psi bra psi. Let me expand it. So kth psi is cz kz plus ce kte, and bra psi would be the complex conjugate cz star, and this would become bra psi, and then you have, sorry, it is kz bra z and ce bra e, right? C star. If I open it up, then I will have terms like cz, cz star, kz bra z plus cz ce star, kz bra e plus ce cz star, kte bra z, and we'll have ce star, kte bra e. Now the beauty of this density operator representation is that we can represent it in the form of a matrix. So to represent it in the form of a matrix, so I write rho is equal to, I will explain you how I'm writing it. So I have here term CZ star, then I can write here CZ CE star, and you see CZ star, this one corresponds to, this is the coefficient associated with KZ bra Z, okay, and CZ star, the next term is a C star, it's a coefficient associated with KZ bra E. Then I have term CE CZ star, this is the term associated with Kate E Kate Z, and then we have CE star, this is the term associated with Kate E bra E. Okay, so what you have seen is that the first term here, it corresponds to the row, and this, the other one, is associated with the column. Okay, so as you can see, I hope you are able to see this, that rows are refers to the first term, Kate term, and the column refers to the bra term. As you can make it out easily, just look at it carefully and you will get it. And then I can write this also, I can write it at, this would be CZ mod square, then I have CZ CE star, then I have CE CZ star, and CE mod square. In fact, I can write this first term CZ mod square, this is the density matrix element rho ZZ, and this one is rho ZE, and then I have rho EZ and rho EE. These are the density matrix elements, and also you see that rho ZZ plus rho EE is equal to 1. That means the trace of the matrix rho density matrix is equal to 1. Okay, and also you see that rho is equal to rho dagger Hermitian conjugate, that means that rho is Hermitian. So these are two important properties of the density operator or the density matrix. So these are very important properties. Trace rho is equal to 1 and rho is Hermitian. So a typical two-level atomic system represented by the density operator, let me write once again, I can represent it by this density matrix rho ZZ, rho ZE, rho EZ, rho EE, and where rho ZZ is the density matrix element. In fact, this is the matrix element 0 Z, and also as we have seen that this is nothing but CZ star. Okay, let me actually show you how this I am writing it in this particular form explicitly, because as I write rho ZZ is equal to 0 Z, I can write, let me write rho as Kate psi bra psi. Okay, that is what my rho is. So I have this terms, and if I expand it, first let me work it out, this scalar product of Z and psi. So Kate bra Z and psi is CZ Kate Z plus CE Kate E. If I open it up, let me expand it, I will have CZ is just a number, so let me take it out, CZ bra Z Kate Z, that's a scalar product, and then I have CE bra Z Kate E, and because these are basis states, they are orthogonal to each other, so Z Kate Z, this scalar product is going to be 0 and this is going to be equal to 1, so you will be left out with only CZ. Okay, and similarly you can work it out, scalar product of psi and Z, and this would be the complex conjugate, that would be CZ star. Okay, in this way you can get the all the other terms. That means you can similarly show that rho ZE, for example, that is going to be this matrix element, that is your 0 E, and you can prove that that is nothing but CGCE star. Okay, now any two-level or two-state quantum system can be represented by this density matrix, 2 by 2 density matrix, any arbitrary general one I'm talking about. Here specifically I talked about a two-level atom, but let us consider any two-state system, general two-state system. Isolated two-state system can be represented by this density matrix, rho 1 1, rho 1 2, rho 2 1, rho 2 2. These are the matrix elements, where rho 1 2 is the matrix element 1 rho 2. By the way, here I am taking the basis vectors as K1 and K2. I am considering a general case. And similarly, you have say rho 2 1 is 2 rho 1 and so on. And so on. Okay. Now rho 1 1 is actually, you have 1 rho 1, and this is, if I open it, I have Kate psi bra psi, that is what is rho 1. And these are, you see, these two terms are basically, these are numbers, so I can write it as, and they are complex conjugate of one another. So this would be simply 1 psi mod square. So this is what? This is nothing but probability. Rho 1 1 represents the probability of, getting the system, probability of getting the system which was in an arbitrary state psi, getting the system in the state in the state K1, right? This is what you have. Similarly, rho 2 2 is projection of psi on 2 mod square. This is again the probability of getting the system in the state eigenstate or the basis state K2. So what you see, that rho 1 1, rho 2 2 are basically represents populations. These two diagonal elements in the matrix represents population. On the other hand, what about the off-diagonal elements? Off-diagonal elements, suppose these off-diagonal elements are not equal to 0, if the non-zero there, that means the system, if they are non-zero, the system is in a coherent superposition of K1 and K2. They are in a superposition state of 1 and 2, and the similar meaning is for rho 2 1 as well. In fact, rho 1 2 is, in terms of the amplitudes, it is C1 C2 star. C1 and C2 are complex quantities, so I can write it in this form also. If I talk about the amplitudes modulus C1 C2 and their corresponding phases, I can write. For C1 I have mod C1 I phi 1, and for C2 I have mod C2. Then because C2 star, its complex conjugate would be minus I, its phase term would be minus I phi 2, which I can actually write it as C1 mod C1 C2 e to the power I phi 1 minus phi 2. And what it means, it implies that rho 1 2 gives the information about, it gives the information about the relative phase of different components of the superposition, So it basically gives the relative phase between the state 1 and state 2 in this case. And this is what the physical meaning of various elements in the density matrix, and this is very important. So to conclude, I would again stress that the diagonal elements represents population, and the off diagonal elements, say row 1 to row 1 row 2 1, they represents phase, or yeah, so phase. Okay, they gives the phase information. All right, now I can actually prove, here I have just showed you that trace row is equal to 1 just by an example, but I can prove it in general. A general proof can be worked out, so we will do that in the problem solving session, or you can just try it. You please try using this general definition of the density matrix, which is P alpha, say psi, Kate psi alpha, Bryce psi alpha. Use this, and then from using this, please try to prove that trace row is equal to 1. Okay, this is going to be a good exercise. Please do that. Let us now discuss how to distinguish a pure and a mixed state using the density matrix formalism. For a pure state, rho is equal to Kate psi bra psi. That's for a pure state. So if I take rho square, then I have, for first row I have this, and for the another row I will have Kate psi bra psi. Now this, you can see, this is equal to 1 because this Kate psi is normalized, so I will be left out with Kate psi bra psi, and this is nothing but rho. So for a pure state, rho square is equal to rho, and if you take trace, because trace rho is equal to 1, this also implies for the case of pure state, trace rho square is also equal to 1. So this gives a way to quantify a pure state. If you just know the density operator or the density matrix rho, then you take rho square, and then if you take the trace and if you get it to be equal to 1, then you are sure that that's a pure state. Okay, what about the mixed state? For a mixed state, we have rho is equal to summation P alpha Kate psi alpha bra psi alpha. Let me again take rho square. Rho square would be, for the first row I have, say alpha P alpha Kate psi alpha bra psi alpha. For the another row, let me write here sum over beta P beta psi beta Kate psi beta bra psi beta. And if I open it up, let me write here, let me take the summation here, sum alpha, sum over beta, P alpha P beta, then I have Kate psi alpha psi beta, and this psi beta, right? And then because psi alpha psi beta, they are orthogonal to each other, orthonormal to each other, so this is going to be delta alpha beta. So let me now write here it is sum over beta P alpha P beta, because this is just a number, so let me take it to the other side. I have Kate psi alpha bra psi beta and delta alpha beta. Now you know that delta alpha beta, that is equal to 1 if alpha is equal to beta, and delta alpha beta, Kronecker delta alpha beta, that is equal to 0 if alpha is not equal to beta, right? So using this, immediately I can write sum over alpha P alpha P alpha, that is P alpha square, because beta is equal to alpha now I'm writing. So we'll have psi alpha, this kth psi alpha, bra psi alpha. All right. And so this is my rho square. Now let me take the trace of rho square. So trace of rho square would be, so let me take sum over gamma. So this is bra psi gamma, and then rho square I have to write here as summation alpha, sum over alpha, P alpha square, kth psi alpha, bra psi alpha, and this is basically multiplied by, from the other side, psi gamma. And again this scalar product is nothing but delta alpha gamma, Kronecker delta alpha gamma. So using that you can hopefully see immediately, it's very easy to see that you are going to get sum over alpha P alpha square. So for the mixed state you are having trace rho square is equal to sum over alpha rho alpha square. This is a classical probability P alpha square. So it is, you know that this has to be less than or equal to 1. So for mixed state actually this is less than 1. Trace rho square is less than 1. So this is the way you can distinguish a pure state and a mixed state. So for a pure state, trace rho square is equal to 1, and for a mixed state, trace rho square is less than 1. Let me stop here for today. We'll continue our discussion on the density matrix formalism in the next lecture. See you then. Thank you so much.